You look different. Okay. So yesterday we started this problem, and Mr. Henderson kind of derailed us and kind of, made it so that we couldn't actually do the problem, and so I'm totally blaming Mr. Henderson at this point. He did. So, yeah, I had a huge brain fart yesterday, and I apologize. Now, what we would need to understand, let's just forget it ever happened. What we need to understand is that whenever we have a mass on a spring, and we pull it, let's say its equilibrium position was here, and we pull it, we get a restoring force. That's what my brain was trying to tell me yesterday, but was having trouble doing so. I displace it this way, a certain distance, delta x, or just x. Sorry, I'm getting my physics classes mixed up right now. And I get a restoring force in the opposite direction. Okay. With that understanding, if I take this pendulum from its equilibrium point and displace it this way, I get a restoring torque. Okay? If I displace it a certain angle theta, if I define this direction to be positive, a positive angle theta, then my responding torque will be negative. Okay? So I'm going to do that. I'm going to define, what would that be? I'm going to define out of the board as the positive direction. Okay? Meaning that the torque, the restoring torque, will be negative. It will be in the negative direction. It will want to cause, it will be the z-axis or whatever. It will cause rotation in the opposite direction. That's why my notes were messed up, and I apologize for that. Again, Connor's fault. So, with that being the case, I have the torque created by mg. There's also a tension force here, but the tension creates no torque because the tension points at the axis of rotation. And again, that's like pushing a door's hinge and wanting it to close, right? It's not going to happen. So, mg is the only force creating the torque. And I'm just going to call the length here L. The lever arm for the torque will be L, right? It is R technically, this is a general vector, but R has the same length as the length of the pendulum. So I can use Newton's second law. The net torque is rotational inertia times angular acceleration. Oh, I thought I hit enter. Timothy, are you there? Something's happening. Sullivan, are you there?
Yes, sir.
Okay, I think Timothy's having connection issues. So the net torque here, now the torque again is going to be negative. I'm just going to say that the angle, my displacement, just like with the masses, you displace it one direction, you get a force in the other direction. I displace it, I give it an angular displacement, I get a torque in the opposite direction. So if theta is positive, then my net torque is negative, right? The negative torque due to mg is going to be rotational inertia times angular acceleration. Well, my torque, remember torque in general is R cross F. The magnitude of the torque. By the way, you can indicate magnitudes if you're being consistent with your vector symbols. You can indicate magnitudes just by writing the thing with no vector symbol above it, right? So then that would just be RF sine theta. So this restoring torque would be negative, and then it would be R, but we know R is just the length of the pendulum L, times the force, which is mg, times the sine of the angle between them. And that's going to equal, is he trying again? Timothy's having trouble getting on. And that's going to equal the rotational inertia. Well, we know the rotational inertia for a point mass. Rotational inertia for a point mass is mr squared. So here it's going to be ml squared times the angular acceleration. Is he there? All right, he's in. Everyone brought mass to the party. Everyone also brought an L to the party. So I get negative g sine theta equals L times alpha. I'm not messing up again, am I?
No, remember the sign.
So how do we deal with the sign? Because remember our general equation. Am I recording, please? Yes. Our general equation is the second derivative of position with respect to time plus some constant which can be equated to omega squared times the original position equals 0. We expect a pendulum to behave like a simple harmonic oscillator. We are trying to show that that is in fact true. Our problem is that we have the second derivative of the position function, but we don't have just a position function. We have the sine of the position function. But what did we talk about yesterday? For small angles, this angle right here, what is it, opposite?
Equal to sine theta.
Yeah.
Yes.
Wait, what? Approximately. Because if we have this arc length here, S, this is the opposite side, this is the hypotenuse. That's how we did that one, right? Yeah. The sine of theta is equal to the opposite over the hypotenuse. For small angles, the opposite side is about the same size as S. So it's approximately equal to S over the hypotenuse. But the hypotenuse is also very close to, in length to the adjacent side A for small angles. And we know that S, from our knowledge of geometry, is R theta over A. But R is also the same size as A, right? Approximately. This is approximately equal to A theta over A. So A cancels, and so you get that the sine of theta is approximately equal to theta. And if that still gives you trouble, let me show you something. And like Timothy pointed out yesterday, the 3 blue, 1 brown video over this is pretty awesome and pretty illuminating. Where's my mouse?
Somewhere. At least one.
That was so incredibly helpful, Alex.
Under there.
I was thinking of hand measure, right?
I don't know. So here I have graphed y equals x and y equals the sine of x. And so if we just replace x with theta, then really they don't start diverging until you're about halfway to 1. Well, 15 degrees, because that's what we say, sine of theta is approximately equal to theta. Or last year we talked about the period of a pendulum you can approximate as, you can use the period equation for a pendulum as long as you're dealing with angles smaller than about 15 degrees. 15 degrees is about a quarter radian, so it's right there. So they're pretty much the same on this interval. And then that 3 blue, 1 brown, when it talks about how you get that weird expression for the sine of the angle, well, you just start converting this straight line into a polynomial by adding terms. And how do you figure out what those terms are? You just do a little bit of derivatives, right? It's really not that complicated. It's just more tedious than anything. But you end up taking this line, you start curving it around based on where the derivatives are 0, where the slope of the actual function is 0. The more terms you add, the more your function will exactly start overlaying the sine function itself. It's pretty interesting. I would definitely recommend watching it. It's 3 blue, 1 brown. Uses Taylor series expansions to do this. You can do this with e to the x. You can do this with cosine, tangent. You can do this with all kinds of functions. And you can approximate those functions essentially just as polynomial functions. Then if you do those polynomial functions in just a certain way, doing series expansions, then you can get expressions for those. And that's how they didn't have calculators back in the day where they could just put the sine of 60, right? They actually had to have it written down in a book. And to fill that out in the book, they had to determine those things using that much more iterative and complex process. Good stuff. All right. So, with our small angle approximation, we can then say that sine of theta is approximately equal to theta, so I have negative g times theta. As the pendulum swings back and forth, theta changes. So theta is a function of time. That's going to equal theta, or L, times, well, angular acceleration is the second derivative of our angular displacement function with respect to time. Now we're getting somewhere, right? Yeah, we'll divide both sides. But I'm going to first get them all on the same side, both terms on the same side. So I'll have L times the second derivative of our angular displacement function with respect to time, plus G times our angular displacement function equals 0. Divide everything by L, right? And I get the second derivative essentially of position with respect to time plus G over L times our position function with respect to time equals 0. Not respect to, as a function of time equals 0. Notice that's the differential equation for simple harmonic oscillators, right? It doesn't matter what the coefficients are, they're meaningful. But if you can write the equation like this, you can solve it with a sinusoidal function, with a sine or a cosine function. And then you can use the coefficients in front of the position function term in order to determine the angular frequency for that oscillator. So if I go from that standpoint, I have this equation. Well, I know that anytime you have an equation like this, as we showed yesterday, omega squared is equal to the... We can write the solution, right? And then put the solution in here and do the second derivative, cross everything out, and then we see that omega squared equals G over L. Okay, so I'm not going to do that again. So we have omega squared equals G over L. Those of you at home, except for the people that are watching now, Dan Fullerton's video covered that. So omega squared is G over L. So obviously omega is the square root of G over L. The period is 2 pi over omega, which is 2 pi divided by this, which is 2 pi times the square root of L over G. And what was our formula for the period of a pendulum last year in AP Physics 1 and also this year in AP Physics C? It's that. I think. Let me verify that. Yes. TP is 2 pi times the square root of L over G.
That could have solved the toilet paper crisis.
Yes. Which there might be another one looming from what I've heard.
So let's jumpstart by buying one toilet paper.
Just punch that into the calculator and it'll give you a roll of toilet paper.
Just buying.
It's kind of weird, but yeah, it's true. Cool beans? Feel it?
Feeling it.
It's good stuff, huh? Good stuff.
That's why you have to have a degree in physics to be able to work it like Sherman.
All right, can we talk about another type of pendulum?
If you want to.
Yes, of course I do. I'm trying to redeem myself. Okay. Let's talk about, let me bring it over here so the people at home can see, this kind of a pendulum. These are the more useful ones.
Stick pendulum.
Pendulum.
Stick chewing.
It's a physical pendulum, is what it's called.
Stick.
What?
It's a stick.
Yes. That is my enforcement stick. Watch yourself. So, that's what? Yeah. It's for striking unruly.
Calculate the period of this.
So we can do the same kind of treatment for a physical pendulum. Understand that most real pendulums that are useful are physical pendulums, grandfather clocks. What are they? They're literally designed to have a period of like 1 second or 2 seconds, right? And so, does anyone have a grandfather clock at home? Like, modern ones have lights and fancy stuff in them, but like old school grandfather clock pendulums, they're not electric, right? They're very sophisticated, but you have to literally go in and pull weights up or crank weights up and then give them potential energy, and then they slowly lower over long periods of time. And as they lower, the reason that they're designed that way is because they give the arm, because that thing eventually stops. The pendulum eventually stops moving. But if you want it to keep time, it's got to keep moving. And so that's how grandfather clocks work. They're tall because they have the weights that must fall over time in order to keep the pendulum swinging, to keep it from losing all its energy. So very useful there. Torsional pendulums, watches, springs and watches. Have you ever looked at the insides of a watch and you see that the coiled up spring? Right? You get twist on them and then they kind of oscillate back and forth. Those are like pendulums. They'll operate as simple harmonic oscillators, just like that spring over there. So a lot of stuff. Second semester, when there's a certain type of circuit that we'll see is like, oh, well, that's a simple harmonic oscillator as well. Same type of equation, only with electric fields or electric currents and stuff like that. Alternating current that comes out of the wall, that oscillates simply harmonically, or however you want to say that.
Basically, electricity is like matter, but
Yeah, and much more complicated. Yeah.
So whenever we get into like electricity and magnetism, can we make a coil gun?
No.
Can we experiment?
I have a ring launcher that kind of works like that.
Can we experiment with the police officer's taser?
Like,
Not, probably not.
Ah.
I'll ask him, but probably not. Okay. So let's say we have a physical pendulum that's rotated about its end. Again, for small angles, I'm exaggerating the angles just so it's easier for me to draw it. But for a physical pendulum, it's going to be different, right? The restoring torque, I give it an angular displacement this way. But the weight force is drawn from the center. Weight force is drawn from the center. If the pendulum itself has a length L, that's not the lever arm. The lever arm will be this guy, which is technically R, but I can also label it as L over 2, right? But everything else is the same. Everything else we do the same way. Net torque, rotational inertia times angular acceleration. If I gave it a positive angular displacement, I get a negative restoring torque. So I get negative lever arm, L over 2, times the force, which is mg, times the sine of the angle between those, equals rotational inertia for a rod rotated about its end, as we all memorized, right?
I think
It's 1/3 ml squared.
Nice!
Next amount.
1/3 ml squared times angular acceleration. Everybody brought mass to the party.
And
I didn't.
Oh yeah, I don't know. Well, no one invited you. I'm sorry, that was mean. Oh wow. I didn't mean that. Don't tell him.
yeah, you did.
So I have negative g sine theta in the numerator over 2 is going to equal, over here I have L over 3 times, and then the angular acceleration, times angular acceleration. Oh, actually, let me do it this way. My bad. This is Connor's fault. No, this is Timothy's fault. He's not here, so I'm gonna blame him.
I'm here.
No, dang it.
Bradley's there? Bradley's not there. No, it's Bradley's fault.
Let's blame Bradley. Let's call this. I want a general equation for the reason I messed up. I'm digging into it too much. I want a general equation for the period for a physical pendulum. Okay. So I'm just going to call the distance from the pivot point to the weight force vector d. And you can expand this out. We can go through all this and we can expand all this out afterwards in order to come to specific conclusions. But I just want to get an equation for the period for any physical pendulum, because this is not on the formula sheet. So it's something that you might want to commit to memory. So the net torque here is going to be the lever arm d times the weight force mg times the sine of the angle between them. That's negative. That's going to equal the rotational inertia. I'm just going to leave it as I, because that could be the rotational inertia for any object regardless of shape, times the angular acceleration. Sine of theta is approximately equal to theta by the small angle approximation. So I get negative dmg theta equals I. Alpha we know is the second derivative of theta with respect to time. You can write theta as in function notation if you wish. I'm going to do it slightly differently here just to show you that you can do both. I want to get this to look like the differential equation, the form of the differential equation where there's no coefficient in front of the second derivative term, so that we can then get our angular frequency. So when I do that, I'll have d squared theta, second derivative of theta with respect to time, plus dmg over I times theta equals 0. Right? And there we got it. We got our differential equation for simple harmonic oscillator, where omega squared is simply the coefficient in front of the position function. So omega squared is just mgd over I. So omega is the square root of mgd over I. And so the period for a physical pendulum, so I'll put TPP, is 2 pi divided by this guy, 2 pi over omega, which would be 2 pi times the reciprocal of that, which is the square root of I over mgd. So that's the general equation for the period of a physical pendulum. It could be a rod. It could be a rod rotated about any axis, any point within the rod. Just know that you got to figure out, if for specifics, you got to put in the actual rotational inertia for the object. You got to put in the actual expression for the distance, if it's L over 2 or L over 4 or anything like that. But then you can do that. This one's not on the formula sheet. So you might be asked to derive it. You might be asked to just use it, and then you'll have to know it. Cool beans? Yes.
They feel kind of lukewarm still.
Okay. Can we do one more?
Yes. Oh, you have my permission.
Oh, thanks. So kind. This is one of my favorite ones. I mentioned it yesterday, but now let's actually do it. So if you remember yesterday, long ago, long ago.
I'm gonna be honest, I don't remember yesterday.
I barely do.
At all?
Like I remember this
Yesterday was Wednesday, right?
Thursday.
This week was too long.
Tell me about it.
Okay. So first of
Okay, so we got the Earth, we dug a tunnel through it, and then we throw Trenton in. This is what Trenton does. There's clouds out in space for some reason.
Trenton's got a big mass.
Yeah.
I don't have a big mass.
Okay. So that looks like simple harmonic motion, correct?
Yeah.
All right. So let's determine it, and let's determine how long it takes to fall through the Earth if we were to do this.
Okay.
Now remember, this isn't feasible because the deepest tunnel we've ever dug, and I think it was just for scientific purposes, the deepest mine we've ever dug, really I think the deepest we go is into mountains, but if we're going down below sea level, the deepest hole we've ever dug is about 8 miles, I think. And even at about 8 miles, it gets too hot, and the pressures are too big, and it's not safe for people. And so that's 8 miles down, right? The crust, the lithosphere of the Earth is like on average 50 miles or something like that. So they're never even going to get down to the mantle.
20 miles.
Is it 20 miles?
I've
I'm thinking kilometers. I'm thinking kilometers. Yeah. What?
I've heard anywhere between like 20 and...
Oh, it varies. It for sure varies, yeah. Bottom line, not possible. But if we could dig a tunnel through the entire Earth and throw Trenton in, then he would act, if we neglected air resistance as well, and assume that he didn't like bang the sides of the tunnel on the way down and lose energy that way. He would just oscillate back and forth as a simple harmonic oscillator. And think about it, because I shouldn't have turned this off. I think I turned off algorithm too. Oh, jeez.
Oh,
Sullivan, man. Because you can think, as this oscillation is happening. And let me actually show this to you. Because this is something that you're just going to have to take my word for now. But when we do this kind of a problem with charged spheres, uniformly charged spheres that have charge throughout their entire density, and talk about how the electric force on another charge as it moves within that charged sphere changes, we'll do this as a problem. It just requires a little bit more calculus than we've done so far. So if I have this object right here, Trenton's right here, he feels a gravitational force, right?
I sure hope so.
Hope so. Just intuitively, do you expect that gravitational force to be larger or smaller than the gravitational force up here?
Bigger.
You expect it to be bigger? Why?
Smaller.
It'd be
Oh,
Timothy says smaller. What?
So why is it bigger?
It would actually be smaller.
Yeah.
Think about it this way. And this maybe is what Timothy was thinking about. Down here, up here, you have the entire Earth pulling on you. Right here, you have some of the Earth below you pulling on you, but then you have Earth above you pulling on you upward. Right? It turns out that when you're at this location, and say the center is right here, you can calculate the gravitational force here as if this mass was the only mass exerting a force on you. You can ignore everything outside of the sphere that you're on the surface of, anytime you're inside the Earth. Conceptually, it kind of makes sense, just because when you're here, this stuff is pulling up on you. But we will prove that that is true with electric charges. Consider this to be a charged sphere with uniform charge in it all the way through it, just like this is a large mass with the uniform mass in it. And then as a charge, we put a charge in different locations within that sphere. The force on it here, that charge here, is due only to the sphere of charge underneath it. Okay? Neglecting everything else that's outside of that sphere. We will prove that that's true. Right now, you just got to accept it. You just got to accept that when Trenton is here, the only force that you can approximate, because there's force on him from this location, but it's negated by forces on him from other locations. And you can add up all the forces that are acting on him, and it's identical to the force that would act on him if he was just right there.
Basically, if you want to prepare someone for a moon trip, you could just put them a few thousand miles deep into the Earth, and they'd
Preparing for what?
a moon trip.
Yeah, because that's easy to do. Yeah.
It's
All
a
right.
giant elevator.
So you got me on that? You just got to take my word for that now. But again, we will learn how to prove that with some more sophisticated mathematics next semester.
So, the second semester in AP6C is just kind of like AP6C2, electric fluid.
Yeah. Totally different class. Yeah. Some schools do mechanics in 1 year and electromagnetism in a whole other year. So that's why we move so fast in here. Okay. So let me draw the Earth with the tunnel in it.
The function is more like a spring than a thing.
Oh, that's a
That's
good one.
really
Really good, actually.
Now,
You know there's a circle drawing competition?
have you seen that video of that professor that does like perfect circles?
He does like goes like that. Okay. I'm going to follow my notes this time, okay?
Probably a good idea.
All right, so up here, here's Trenton. Up there, he's got gravitational force on him. And then at some random time, after we've dropped him, he's here, and he now feels a smaller gravitational force. Because there's less mass, right? Only the sphere of influence is the only thing that's influencing him is that sphere that he's actually on the surface of right here.
Just like in Chinese culture, the sphere of influence.
What's that?
Just like in ancient Chinese culture, the sphere of influence.
Yeah, exactly. And then, so if this is the center, the position vector, I'm going to call little r. That position vector is equal to the radius of that sphere of influence, right? Now we also have the radius of the Earth, the big one. We'll be using that as well. Okay, so I've diagrammed my situation. We'll call this MT, that's Trenton, and this big guy is the mass of the Earth. Okay. All right. Now we will be using this in a minute, but I'm just going to write it at the surface. The force, I'll put Fg, comma S, force of gravity at the surface. We got to be a little more careful here. For big kids now, force of gravity is not just big G m1 m2 over r squared. It is negative big G m1 m2 over r squared, because the position vector is always drawn from the center of the Earth, right? When we use Newton's law of gravitation, we use r, this is r, and the force is this way, right? If I want to know the force on this guy, I got to specify his position relative to the first guy with a vector, and the gravitational force is in the opposite direction, right? And so that force is actually in the negative direction with that particular vector, with respect to that position vector. So the gravitational force is negative big G, mass of the Earth, mass of Trenton, over the radius of the Earth squared. Recording, right? Yes. We good with that? Okay, so put a pin in that. Put that in your equation holster. We'll come back to it. That's how Mr. P does it. So let's talk about this gravitational force as Trenton is falling through the Earth. I'm just going to call that Fg. That's going to be negative big G mass of Trenton, and I'm just going to call the mass of this guy, the smaller guy, just m. I'm just going to call it little m. Over the radius of that sphere squared. So I called that little r in my diagram. Now we also know another expression for the gravitational force. Gravitational force is always equal to mg, right?
Yeah.
Is that here? And if that is the net force, then it also equals mass times the acceleration. So I wanted to determine the acceleration of Trenton as he's falling through the Earth. An expression that has the acceleration, because again, we're looking for the second derivative of position. So I can say that I can take that MA and put it in over here. And when I do that, I'll get mass of Trenton times his acceleration equals negative, and we expect the acceleration to be negative because it's down, and we're making our measurements from the center of the Earth, times mass of Trenton times the mass of the sphere of influence over r squared. And obviously, Trenton doesn't matter. So I'm just kidding. Everybody brought Trenton to the party, right?
No,
So-
it doesn't matter.
So I have an expression for the acceleration. It is negative g m over r squared. I could, because I know I'm doing this differential equation stuff, write the acceleration as the second derivative of our position function r, lowercase r, with respect to time. Not d squared x, right? Because we're talking just general r, general position. We could use y, I guess, but when you're talking the Earth, there's really no up, down, left, right. So we'll just use r, the general position vector, equals negative big G times the mass of the sphere of influence over r squared. Does this match our differential equation for simple harmonic oscillators?
Or, well, it is the...
It doesn't,
No.
because r is above.
It does not. Yeah, r's in the denominator and it's squared. So obviously this was an exercise in futility, right? So let's just throw in the towel.
Okay.
No!
Alright, time to go home then.
So as is often the case with this more difficult calculus-based physics type stuff, we need to talk about mass densities. Okay? Not in the way that we did before, but we are going to talk about mass densities. First of all, we need to assume, because if we don't, it gets even more fantastically complicated. We need to assume that the uniforce is uniform mass density. And if that's the case, then I can write the mass density rho is equal to the mass of the Earth divided by the volume of the Earth, which is 4/3 pi times the radius of the Earth cubed. Okay? if the uniform is Earth, if the Earth is uniform mass density, then the density of this smaller sphere should be the same density, right? So this should also be equal to the mass little m over 4/3 pi little r cubed. I can write that equation. You with me? Everyone brought 4/3 to the party. Everyone brought pi to the party. And everyone brought pi to the party. Oh, it's been a long week. So we have mass of the Earth over radius of the Earth cubed equals mass of the smaller sphere over its radius cubed. Ooh, what happens if we solve for m and plug it in here?
And we'll get r
Oh.
inside.
So I get little m equals r cubed, mass of the Earth, over radius of the Earth cubed. So if I plug that in for m here, I get this negative g over r squared times r cubed, mass of the Earth, over radius of the Earth cubed. And then as Alex pointed out, now we got the second derivative by itself. We got some constants and the position vector. The second derivative of position, constants, and position, they're on opposite sides, but this one's minus, right? It's got to be added together equals 0. It's got to be. If it's minus between them on one side, it doesn't work. It's not simple harmonic motion. But it works here. So we can rewrite this as second derivative of position with respect to time. And I'm going to add this term to both sides, so it'll be plus big G, mass of the Earth, over radius of the Earth cubed, times R equals 0.
And that also gets rid of little m, that's also not a constant.
Right. Exactly. That's yeah, perfect. Thank you for pointing that out. Because yeah, m changes the whole time. Little m changes the whole time. So that can't be in there. We the only thing that can vary in our differential equation for simple harmonic oscillators is the position. Everything else has to be a constant. Good point. Now what else we can do? That's not grammatically correct. Is remember that we can always, and real quick, we can look at what we did here. The gravitational force is always given by Newton's law of universal gravitation. It's also given by mg. So I can say, just cut this off, it's just taking up space. I can say that the force of gravity on Trenton is big G at the surface times the mass of the Earth times the mass of Trenton over the radius of the Earth squared. That also equals the mass of Trenton times G at the surface, right? G is 9.8 G. Of course, everyone brings Trenton to the party because he's that popular. And I get that G, you might be asking why I'm doing this, but look over there and you might see why. G, the acceleration due to gravity at the surface of the Earth, which is a constant, is equal to big G times the mass of the Earth over the radius of the Earth squared. It's just a way to further simplify our differential equation. So I have second derivative squared, second derivative of position with respect to time, plus, can't I take a GME over RE squared out and just replace it with little g?
And then just do G over RE.
Yeah. So little g, the acceleration, the acceleration due to gravity at the Earth's surface, divided by the radius of the Earth, times the position, equals 0. Little g and the radius of the Earth are well known. And just like we can do with any differential equation, or any simple harmonic oscillator differential equation, we can just set omega squared. We can do this. We can have our position function, which will be sinusoidal. Do it just like we did yesterday and end up with omega squared equals that coefficient. So omega squared is g over the radius of the Earth. Omega is the square root of g over the radius of the Earth. The period is 2 pi over that, or 2 pi times its reciprocal. What does that period tell you? That tells you how long it would take for Trenton to fall to the other side and then to come back. So half of that would tell you how long it would take you to fall all the way through. A quarter of that would tell you how long it takes to fall to the center. Yeah.
Well, what happened to the negative of FG?
Oh, here I'm not concerned about the position. Here I'm just concerned about magnitude. Good point, though. Stop asking questions that make my brain hurt.
I'm sorry.
All right, so you feel good about that? So let's actually determine it. Let's determine it. 2 pi. We all know the radius of the Earth, right? What's the radius of the Earth?
A lot.
It's like 6.3 million 6.3 million meters, I think.
That's a lot.
It's at least 6 feet long.
It's only 6 feet.
I'm taller than the radius of the Earth.
Wow.
It's about 63 hundred.
6.378 times 10 to the 6. 6.378. So 6.378 times 10 to the 6th divided by 9.8. Do that in your head, right, Joel? Okay, I did something wrong.
Get something too low.
I have something too big.
It is in seconds.
Oh yeah, that's in seconds. That's right.
So it probably makes sense that it's huge.
So divide by 60. 84 minutes.
Honestly, I thought it'd be longer.
Yeah, that's a long distance. That's in miles.
Well, I guess also since there's no air resistance, that
That's about 8,000 miles.
yeah.
8,000 miles, and that's like a 1,000 miles a minute. Right? No, it's not. I can't do basic math.
Oh, wow. It would take me less time to fall through the Earth than it would to go to Galveston.
Yeah. Well, you start off with very slow speed, but you pick up a lot of speed, and by the time you get to the center, you're moving real fast.
And like I was saying, since there's no air resistance, there's no maximum speed you're gonna hit. You'll just keep speeding up until you speed up until you hit the center.
Yeah. And then you start slowing down on the way out, but you're moving fast then. Now, check this out. Check this out. Do I got time? Yeah. Let's say that we... Have you guys ever seen Spaceballs?
No, but I know what it is.
Oh my
I
god.
don't want to have.
Nice.
You look so like devastated.
I am. You haven't seen Spaceballs? Okay, so there's a part in Spaceballs where they suck all the atmosphere off of a planet. So let's say we do that to the Earth. And we have an object orbit the Earth, but at ground level. Essentially the level that we drop Trenton into the hole at. Okay. And so it's going to orbit the Earth at an orbital distance equal to the radius of the Earth. Okay. And so I'm going to calculate the period of that orbit. And so to do that, I say that the gravitational force is big G. Say it's Trenton too. We throw Trenton horizontally so fast that he's orbiting the Earth now. So mass of the Earth times the mass of Trenton over the radius of the Earth squared.
That'd be terrifying.
Yeah.
You're just like walking around and you see someone just like 20 feet above.
As you'll see, he'd be moving very fast.
It's a bird. It's a plane.
And so that's also, though, because he's now in circular motion, mass of Trenton times his speed squared over the radius of the Earth, right? So Trenton cancels, radius of the Earth cancels. So I get big G, mass of the Earth, over radius of the Earth, equals speed squared. Well, we have an expression for speed squared in terms of the geometry, or for speed. It's just 2 pi radius, in this case radius of the Earth, divided by the period. So I'm going to plug that in there. So big G, mass of the Earth, over radius of the Earth, equals, and that gets squared, so it's going to be 4 pi squared, radius of the Earth, squared over the period squared, right? I feel like I'm going to mess this up.
Believe in you.
I can divide both sides by 1 Earth radii. Right? Can I do that? Because then g me over re squared is, again, little g. So g is 4 pi squared radius of the Earth over period squared. I can flop the t squared and the g, so I get t squared equals 4 pi squared radius of the Earth over g. And I take the square root of both sides, and I get that the period of orbit, the orbital period, is 2 pi times the square root of the radius of the Earth over g. And if you're not impressed by that, you forgot
That would be
something.
Very fast.
Here, let me put a red box around it. You guys haven't noticed yet?
It's the period is the same.
Period, same period.
Oh my god, you'd be moving so fast. 84 minutes.
Yeah. That's like,
1.4 hours all the way around though.
yeah.
Zoom.
Isn't that interesting though?
Yeah.
The time that it takes to go whoosh, whoosh, same time that it would take to go.
Well, that makes sense why there's omega in the formula then. Why for simple harmonic.
Yeah.
So we should
So is
say,
that
Simple harmonic motion, straight line, but yeah, oh, there's a connection there that I totally was thinking of and was totally going to point out.
yeah, exactly.
Yeah, there's omega.
so we could get like Trenton and drop him through and then throw Alex at that same speed and they'll just like hit each other.
Yeah, for sure. That's what we're going to do on Monday. We ran out of time today, but we'll do that on Monday.
Yes, obviously, me and strings are both perfectly elastic objects.
Of course.